Okay.
So, and along those lines, so the first question I wanted to kick off with, and I'm not sure whether I'm going to stick to the questions depending on how the conversation goes, is so you are vocal in your post on agile engineering, and we've seen successful companies in that space. And so why are so many organizations struggling with adopting it?
Okay, well, first of all, great question. I would love to give some context on what this change is, because I don't think the systems engineering community yet has quite got a good definition on exactly what the change is. A lot of people say agile is 2 week sprints and is software and is MVP, and that's not really the case. So maybe let me take a step back and give a broad view on context on what this change is and why it's such an important change. So the first thing to say is we really see a once in a generation transition happening in the systems engineering community right now. It's the last time a change on this scale happened was probably in the 1960s when systems engineering was sort of forming in the early days. And this change is from a more traditional, top-down, waterfall orientated 10-year design cycle where everything is about working with external contractors and being very rigorous to a much more agile and iterative workflow. And what this means is it means two things. The first thing is it means there is a mix between top-down requirements management and bottoms-up design. So early on, when our systems were less complex, we could basically mandate all of our requirements from the mission level to the system, to the subsystem, all the way down to the component level, and be correct in those assumptions. But as our products have got much more complex, that's no longer possible because our systems are now so complex and so cross-functional that a tiny change in one team can cause complex changes across other teams and other organizations, which then cause complex changes. And more often than not, we've not designed a vehicle of this scale or this complexity. More often than not, we don't fully understand the systems interactions between software and hardware at the start of the project. And these things need to be understood over time. So the first big change in the waterfall to agile, waterfall is largely top-down driven and largely built to avoid change. And agile is largely built to say, we have assumptions in the early days around what our requirements may be, but we are open to learning because change is inevitable. And we probably won't be right around all of our assumptions, our technical assumptions, because we've never built something like this and it's very, very complicated. And as a result, agile teams don't just break requirements from the mission to the system level or the subsystem level, but they actually flow down requirements from L0, L1, all the way down to L3, L4, L5. So you've got full traceability from the mission level all the way down to a specific component level. So that's the first big change. The second big change is to realize that iterative is really the way to go. One of the people that we know very well recently gave this story, which said, if you want to build a 6-inch telescope, it's typically faster to build a 3-inch telescope and then build a 6-inch telescope than it is to build a 6-inch telescope
I
straight
saw
away.
that story on LinkedIn where you talked about that. Yeah, absolutely.
And it's a really great analogy. And what we see the best teams in the world do is they don't start at the most complicated version and try and lock down assumptions early on, but they say, what's the smallest unit of integrated system that I can build to be able to de-risk and learn from my assumptions? And then how do I add layers to that over time, iteratively, to be able to learn and develop very rapidly? And
If
more
I
often than
may,
not, please.
if I may rephrase that from a basically software point of view, it sounds like you're proposing the MVP approach, except
Yeah.
that in software, you can continue to evolve the product. And I mean, in hardware, you simply have to build a second telescope, but the idea is the same. You start with an MVP and you basically build up once you have a functioning system.
That's exactly right. And what you get with that approach, that approach sounds very wasteful. So hardware engineers don't like the sound of this because it says, well, I could build it once, but you're telling me to build it 3 times now. Uh, but actually, if you look at companies like SpaceX and you look at companies like Tesla and you look at the fastest moving companies, This approach is much more efficient than the traditional approach. So if you compare Starliner, which is Boeing's capsule, to Dragon, Dragon has done more in half the time with half the cost. And they've had lots of dragons when they build it and they've learned something from it and they put it away. And this iterative approach sounds slower and sounds more expensive, but in experience, it's been demonstrated to show that it's much faster, much more efficient, and actually much safer to operate in this way.
So I agree with that. And based on that, um, I have to think of their Starship launches. And I mean, what really bothered me was the headline I read the other day: fourth test flight finally successful, which implies that the first three were not successful. So
Mm.
what I think is that we really need a paradigm shift where people really understand that, a blown up rocket is not a failure, it's a successful test because it delivered
Absolutely.
data. So my question to you is, how do we achieve this paradigm shift?
It's very difficult. The core is not to focus on the requirement delivery, but is to focus instead on the learning. So this is one of the things that SpaceX iterated again and again on the live stream for IFT4. They said the payload is the data. It's not the
Yeah.
successful flight. It's not us meeting all our requirements. It's not closing our VOV successfully, but the payload is the data. And if we're able to get really great data off of the vehicle and understand its exact limits and where we're doing well and where we're doing poorly, then we'll be able to design IFT5 or the next vehicle much faster, much better, and much more rapidly. So the core is to focus on learning. And then the next step that you derive from that is, okay, how do we learn as quickly as possible? And then the second big thing that systems engineers find it very tough to do is they need to come out of requirements land, and they need to come out of analysis land, and they need to come out of thinking land, and they need to move into doing land. And that's a very difficult transition for systems engineers that don't necessarily love that. I certainly came from that background. I'm a mechanical engineer by training. I spent my entire early career building analytical models to design rocket engines, hybrids, and liquids. But actually, you learn a lot from just building the smallest amounts, testing it, and going end to end on that, and then building the next one and the next one, and the next one. And if you look back to Apollo, actually, that's a lot of what they did. A lot of what they did is that we need to go to the moon. And to go to the moon, we need to build the Apollo missions. But we can't go straight from here to the moon. So before we go up and have multiple stages and then go around the moon and then land on the moon, we need to be able to go up and have multiple stages and get to orbit. And before we get to orbit, we need to be able to get to like pass the Kármán line. And the fastest, cheapest way of us getting past the Kármán line is to get a missile that we have today, to put a human on the top of that missile and to launch it. And if you think about just the scale of that at that stage, it's insane. But that the fastest way for them to learn was to retrofit a human to a missile, an ICBM, and then to learn as quickly as possible. And that's how we got to the moon.
And I agree with that. I mean, at the time, they did the iterations at a pace that was doable with the technology available. And those were like the different missions, like Gemini came before Apollo and so forth. However, I disagree with the statement that you just gave that systems engineers don't want to get away from the requirements and stay there. I think it's more the fear from the decision makers who
Mm.
feel that, again, like a blown up test rocket is perceived as a failure, which is not. So again, how do we realize this paradigm shift? How do we talk to decision makers and allow them to give the engineers the freedom to do these things?
Yeah. Well, let me give you two or three answers and some context. I think context is really important for our industry because if you look at just today, it doesn't make any sense. The way we do engineering doesn't make any sense whatsoever. But if you understand it in the broader context of the last 20 or 30 years, suddenly you can see why we've come to the conclusions that we've come to. So if you look at where systems engineering came from, systems engineering actually came from early publicly funded missions, space missions. And that was the early days of what I call true systems engineering. And that is typically taxpayer funded. It's typically a mission that we've never ever done before, so very, very difficult. And as a result of those two things, when you've got congressional allocation, or you've got taxpayer money driving missions, and missions that are very, very complex, then and missions that employ lots of people, then you're in this paradigm of needing to get it right first time. Because if a politician spends $10 billion or $1 billion on this big mission and it blows up, that looks really bad. So that's where systems engineering came from. But what we're seeing is we're seeing private companies copy a lot of the sins of publicly funded missions. And that's the mistake. The mistake is assuming that the same rules apply as a private company that's in the game to make money and to build really great, safe, reliable products and to move really quickly. And that's the core shift that we need to make. We need to understand that our goal is to build products that are safe and fast and reliable, not to serve publicly funded missions.
So that explains why startups manage to embrace these approaches, and that large existing old organizations are struggling with that. So any thoughts on, if at all, and if so, how existing large organizations from Boeing to Mercedes to, you name it,
Yeah.
Dyson, how they can make this change?
3 years ago, if you asked me this question, I'd said it was impossible. Um, there's a great principle in science which says the way to create revolutionary change is to let the ancients die out and to let a new generation come in. I'm really glad that I've been proven wrong on this. So I look at certain companies like Blue Origin, who actually started out with a much more traditional conservative model. They hired a lot of VPs from Northrop Grumman and from other traditional aerospace companies, and they bought in that culture, and it almost killed them. And they're currently transitioning to a more agile approach, and they're doing a fairly good job. We will see if it works. We will see if that level of transformation is possible at the scale of a 10,000 person company. But I'm cautiously optimistic about that change. I'd say the easiest, fastest way of doing this is to build a skunk works team. So is to go, hey, transformational change is hard, if not impossible. Rather than taking the existing people and process and culture and trying to retrofit a new way, let's actually build a new team with a new mission to go do something difficult where the only way is agile. And then eventually we will help that team and we'll take that team and we'll seed them into different places in an organization and create cultural change that way. Cultural change happens through a mix of bottoms up buy-in, top down decision making authority, and honestly, a trigger. And that trigger tends to be a big fire, something that's gone horribly wrong, and it requires us to relook at our processes. And my worry is that we're going to wait for a lot of big fires to happen. When I look at companies like Boeing, I'm seeing that play out where you have just fire after fire, failure after failure, recall after recall causing these things. And I hope that we can find a way to do it that doesn't require that level of risk.
Yeah, likewise. And I mean, I look very carefully at what, OEMs are doing, like Volkswagen spinning off CARIAD. And so again, like for the sake of our domestic industry, I really, really hope that they get it right. I would like to shift the focus to a more technical topic. And so you mentioned agile a few times. And so I'm curious whether you think if modeling plays a role at all in this transformation, and if at all, if we're going in the right direction there, maybe any thoughts on system LV2? Are we in a dead end? Are we really on the right track? Is it an enabler? What's going on with the whole idea of making our development artifacts more digital through modeling?
Okay. I've got very strong opinions on this.
I
And
love it.
I am likely to make a lot of people very angry. I went to an Incozy conference a few years ago and I held back my beliefs. And I think it's just fair for me to be quite honest with them. First point here is MBSE is the future. And in my mind, there are two big parts of MBSE. There's model-based definition, so having a view of a system in a model-based way, and then using digital models, analysis tools, numerical models to help augment that and to make that model richer and more alive. So unequivocally, if you look on paper, moving from a document-centric view to a model-centric view is the future, unequivocally. That being said, we think MBSE tools completely missed the mark. We think MBSE tools suck. And if you just show SysML, V1 or V2, to anybody in any other industry, and you say, this is the future of engineering. The future of engineering is this UML-based definition in the 1980s and 90s that we retrofitted into ours, that they will laugh at you. And I've shown it to my friends, and they find it hilarious. And the reason why it's so disastrously wrong is because the core need for MBSE is to build one unified model that every stakeholder across the organization can use as a source of truth. That's the core goal for MBSE. That's why MBSE was created, to build one unified model that everyone can use as a source of truth and everyone can make the main port of contact. And SysML and MBSE tools are so difficult to use that what ends up happening is you need lots of training time, and then you need to think about the ontology, and then you need to think about the structure. And the only people that can use that tool are a few very well-educated systems engineers who then put all the information into SysML v2, and they sit in the corner and they export out to documents, and they send the documents to the rest of the team, which means the rest of the team is just using documents, which means the whole point of MBSE is useless. So for MBSE to be successful, it needs to democratize systems engineering. It needs to give non-systems engineers the same view that a systems engineer has, and it needs to enable systems engineers to graduate level from doing the documentation work to actually thinking about the system in a more holistic way, and to help mechanical, electrical, software engineers all take that same view. So the biggest things that SysML and MBSE tools get wrong is usability. We need to make these tools beautiful and usable and usable for non-systems engineers. That non-systems engineers should be able to pick up an MBSE tool and just go, oh, hey, I understand stage 1 and stage 2. And inside of stage 2, I live in the engines team. So let me click into the engines team, and then let me see the 3 or 4 interfaces across the other systems that I need to talk to. And let me see the latest versions of those interface requirements with interface values. And really become a unified model for the whole team. So more often than not, the people that I see in the systems engineering community, they're the most advanced with MBSE, have a giant wall, and they print out a model and they put it on the wall and everyone can use it. And I'd say printing out a Miro or a draw.io diagram and putting it on the wall is actually a better fit for an MBSE than some of the existing tools like SysML v2. I think the intention behind these tools are amazing, but I don't think the tools are usable for non-systems engineers.
With a lot of the things you say, I do agree. And yeah, I mean, I share that sentiment, especially regarding tools. And Spicy actually had like this like exploding discussion, you know, MBSE is dead and whatnot, and the tools are the problem. But I'd like to pick it apart a little bit, because the tools that are very popular right now are from the 90s, unfortunately. Yep. All the big ones. Yep. So tooling is certainly an issue. But the thing is, tooling is one aspect. The modeling language is another one. Yep. SysML v1 was basically, you know, layer built on top of layer. So the proponents of SysML v2 basically say that the simplification, that the focus on textual annotation and on API will actually make it much more fit for supporting the vision that you described. Of course, only if the tool vendors or startups start to actually embrace it and use it in the right way. Yeah. So basically, you commented a lot on the tooling. What about the modeling language? Is SysML v2 is it possibly the future, or is it another dead end?
I've not got such strong opinions on the actual modeling language itself. Mm-hmm. I think all tools have strengths and weaknesses. Mm-hmm. What I will say is a lot of systems engineers over-index on ontology. Ontology is really, really important, and it gets me excited because I can start to think in layers and philosophy, and I can start to create structure. I can start to create objects and classes. Mm-hmm. But I think it's probably the wrong approach to start with. I think eventually we get there, but I think starting with it turns off a lot of people. And it creates structure and imposes structure where you don't necessarily need it. And this is the whole point. If I had to point out one thing that I wished our community was better at, it's understanding the difference between good process and actually delivering a product. And a lot of systems engineers, especially young systems engineers, read the NASA Systems Engineering Handbook and they read the NCOSE Handbook, and they say, if I just follow all thousands of these steps on 200 of these pages to the letter, then I'm guaranteed to have a good product. And then 10 years later, they follow every single step and they follow every single directive and they write shall statements, and they don't release a good product. And I think what we've seen in other parts is maybe too far of the extreme approach, where we say with zero process, zero steps, zero requirements, we're just going to build stuff and deliver it. And that actually delivers a product, which is great, but is it safe and reliable? And what we've got to find is this nice middle ground. So we've got to find a middle ground where we empower non-systems engineers to have more of a systems mindset, where we help people come into the requirements process and into the MBSE process, and we move it from a silo to something that sits at the heart of the team, that's a live model. And to be able to do that, a systems engineer needs to be able to give up a little bit of control on their team to enable non-systems engineering teams to better collaborate with them.
Super interesting. Yeah, I like your point of view on the structuring, the ontologies, and so forth. And I mean, I come from the software world from the very beginning. That's what I loved. And I remember in the 90s, there was like so much discussion about software components and whatnot.
Right.
And I feel like we are totally repeating what happened back there, because today all this is provided, you just pick the right architecture for your software project and all those pieces fall in place and you can start being productive and shipping working software.
This is really important to say. UML was rejected by the software engineering industry, right? Like
Yeah.
they tried it. It was a great idea and they did not find it useful and it was rejected and it was a and then we've cloned it and we've changed UML to SysML and we've added some features. And we think that it might work for our use case. And I agree with the philosophy and the intention behind MBSE, but I think the specific implementation, we might have missed the mark.
Very interesting. Reminds me of Andreas Willert from Zodius Willert. Not sure whether you know him, who basically said something very similar. And basically, he's working very hard with his company to prevent the same problem happening with SysML. I don't know whether you have time for one last question. And that's basically, I wanted to know what the role of traceability plays in this transformation. And in particular, whether you can also comment a little bit on flow engineering and how you intend to solve this systems engineering problem with your company.
Absolutely. So first of all, traceability is one of the most important things that a systems engineering team needs to get right. It's the reason systems engineering exists, is to help glue all these different functions together and understand when a change happens in one place, the impacts of that change, and to make sure we've got really good process to be able to sort that out. Now, traditional systems engineering only really tracks requirements, and it only really tracks requirements at the mission, system, and maybe subsystem level, but it sort of stops there. So you lose two really important parts of traceability. The first part is requirements at the deeper domain engineer level. So how do we break a system or a subsystem requirement into specific low-level requirements that an engineer can deliver on their V&V? And then number two, it loses design traceability. So we've got all these amazing requirements that say, here's what we need to go do. Then we've got zero traceability other than linking to it, like maybe a CAD model or taking a photo of our aircraft to actually prove that works. And what we're seeing happen is a real need for deeper, more granular traceability as our systems become more complex and more cross-functional. And actually, this is being reflected in the quality control standards that are happening too. So if I take one example that I know very well is nuclear. In the nuclear industry, our new regulations like NQA1 now require full traceability, not just on the requirement side, but to specific design assumptions and specific design parameters that drive different elements of the system. So we think traceability is great, but I think if you're just tracing system mission, system, subsystem level, you're losing 80% of your design and you're losing 80% of the value that comes from having traceability. So we need more traceability, is my bottom line. And then how flow engineering fits into that? Well, great question. A little bit on flow. So flow is building a modern, agile, next generation requirements tool. We're building the platform that systems engineers have been dreaming of. I'd say it's the first modern systems engineering tool that looks like it was built in the 2020s and doesn't look like it was built in the 90s. And our core thing that we get right is we help systems engineers break down requirements from the mission all the way down to the component level, and then have live traceability and live integration with a non-systems engineering team. So what you can do, and I think the other big systems engineering philosophy that has been pushed around for a while is continuous integration and continuous verification. And this is something that was adopted in the software industry and that worked, which is to say, hey, we have requirements which are effectively tests. Can we link these tests to our design? And then the moment a design change happens in one team that affects another team, that affects the third team, that breaks my requirement, rather than waiting 3 or 4 months to find that information out, I can find it out instantly. And rather than maybe dropping a ball, I can actually use the computer to automate all the V&V work and to give me faster information on exactly what requirements are and are not being met. So that's what Flow is doing. Flow is building a next generation requirements tool that links systems engineering and requirements to design and gives you continuous integration and verification across your entire team rather than just one team. We're now working with some of the best engineering companies in the world. We're working with some of the largest and most sophisticated space companies, but also automotive, nuclear, medical device, every major vertical that we operate in, and we're probably working with the fastest and the best teams out there. I'd say we're the market leader of the modern requirements tool space, which is quickly becoming a hotly contested market. But we're probably ahead in every single dimension, and our magic is our product. So if you would like to learn more, please take a look at flowengineering.com, and you can get a very quick sense of our MBSE capabilities, our requirements capabilities, and our integration capabilities.